Hello. Now we're going to talk about area with double integrals. And we did this with our rectangular coordinates, x and y. And essentially we just said that area is defined as the double integral over the region integrated with respect to the area. So in polar coordinates, it's just the same, but what we want to remember is when we define that area in polar coordinates, it's not just dx, dy, or dr, d theta. We have that extra factor. So we say r, dr, d theta. All right, so I encourage you to go back and review the previous video about area in rectangular coordinates from the section before this if you were not or you didn't watch it, but essentially we're just going to define area across some region as this double integral. So let's jump right in and do an example. So for this example, we're going to find the area that lies inside the cardioid, defined by the function r equals 1 plus cosine theta, and outside the circle, r equals 1. So let's sketch our region first so we can set up our bounds and solve this polar double integral. So a circle of r equals 1 is just the unit circle. And then this cardioid, the cardioid has a very nice intersection pattern, creates this sort of heart shape. So we are looking at calculating all of this region. Okay, so let's set this up. Area, my bounds on theta. What are my thetas going to go between? Thinking about this in radians, we would be inclined to say negative pi over 2 to positive pi over 2. Of course, we can kind of simplify this a little bit because, and my drawing isn't perfectly symmetric, but this graph, if you were to graph it in polar mode on your TI calculator, it would be symmetric. We can double it. So we can say from 0 to pi over 2. And I didn't leave space to double that, but we'll say 2 from theta equals 0 to theta equals pi over 2. Setting up my bounds, what are my r's going to equal? My first r would be r equals 1, and my second r will be 1 plus cosine theta. And of course, we write r dr d theta. Remember, when we are working in polar coordinates, this extra r is always going to be in there. We have that extra factor to consider. The derivation of it, I didn't derive it in any of my videos, but it's in our textbook. And I'm sure you could find it somewhere else on the internet if you wanted. So everybody pause, make sure you know how to set up this integral here. Now we're going to evaluate. Integrating r with respect to r, I'm going to have a equals 2. These are my theta bounds from 0 to pi over 2. And that becomes 1/2 r squared. We've got 1 plus cosine theta to 1 integrated with respect to theta. So this 1/2 and this 2, that's lovely that they cancel out. And I've got 0 to pi over 2. I'm going to plug in my first bound, which was 1 plus cosine theta. So I have 1 plus cosine theta, quantity squared minus 1 squared d theta. 0 to pi over 2, I get 1 plus 2 cosine theta plus cosine squared theta minus 1 d theta. Those 1's go away. This is the integral from 0 to pi over 2 of 2 cosine theta plus cosine squared theta d theta. At this point, I can separate these two integrals. I pull that 2 out in front. This is very easy for us to integrate, so I end up with the integral of cosine is sine, so I have 2 sine theta evaluated from pi over 2 to 0. And this second integral here, we use a double angle substitution. We use 1/2 times the quantity, 1 plus cosine 2 theta. So this is equal to 1/2 1 plus cosine of 2 theta. So the 1/2 will come in front. I have 1/2, the integral 0 to pi over 2 of 1 plus cosine of 2 theta. So this first piece here, sine of pi over 2 is 1, sine of 0 is 0. So 2 times 1, this first integral turns into 2. And then I have plus 1/2. Integrating here, I'm going to get theta and plus 1/2 sine of 2 theta. So I've got theta plus 1/2 sine of 2 theta. We need to evaluate that from pi over 2 to 0. And when I plug in 0, that is 0. Sine of 2 times 0 is sine of 0, which is 0. And half of 0 is 0, so that doesn't matter. So we're going to have pi over 2 plus 1/2 sine pi over 2 times 2, that's going to be the sine of pi, and sine of pi is 0. So this simplifies very nicely because all these last 3 terms turn into 0. Again, sine of pi is 0. So I end up with 2 plus pi over 4. That is the exact area of this polar region between the circle and the cardioid. Make sure you email me if you have any comments, questions, concerns. Good luck out there.